at UT Arlington. The topic of my presentation today is going to be about developing the reactive force field ReaxFF for simulations of SiCN polymer-derived ceramics. So a brief background about polymer-derived ceramics. There's a list of notable properties they have. They have an interesting viscoelastic response, corrosion resistance, oxidation resistance, and research has been done in applications like anode material in lithium-ion batteries, low K dielectric thin films, and we're interested in the ceramic whenever the polymer is subjected to a max pyrolysis temperature of 800 to 1300 degrees Celsius during the polymer to ceramic conversion process. And what we get is a material that we can describe as an amorphous glass-like SiBCNO phase. And if there is excess carbon in our starting material, we have a free carbon phase. The glass-like phase itself is a mixture of whatever was also part of the starting composition: silica, silicon carbide, silicon nitride, and boron oxide. And there's been a lot of applications of this and even commercialization. And a lot of the stuff I show here is actually in transportation. The LEAP engine's turbine shroud has PDCs. We can see them in brake discs of motorcycles, in the glow plug of trucks, and these all have been commercialized for those kinds of uses. What we are interested in is the polymer to ceramic conversion process specifically, because the initial starting composition of your precursor polymer, as well as the different treatments that are done, can impact the structure of the ceramic and even parts of the free carbon phase that we are also very interested in looking at. So we choose ReaxFF to simulate these SiCN PDCs. The reactive force field is a classical force field method developed by Audrey von Duhn. Well, he was at Caltech in 2001, and he developed it to simulate hydrocarbons with quantum chemical accuracy. And the famous tagline for ReaxFF is that it bridges the gap between the highly accurate quantum chemical methods and the less accurate classical methods, but the less accurate classical methods that can do simulation sizes in the millions of atoms, which is not something you will see in something like DFT. I mean, you've already seen Dr. Kroll's great presentation. So the selling point of ReaxFF is that it can be trained to have DFT or quantum chemical-like accuracy, but do simulation sizes 10 to 100 times the size of DFT. And even better, ReaxFF can describe reactions better than other classical potentials, because its central principle is that it can describe bond breaking and bond formation, something you may not see in other classical potentials like Tirsoff or so forth. And a lot of work has been done just recently developing ReaxFF for use in silicon oxycarbide PDCs. So work from our own group by Ilya Polymer-Derived was about looking at the pyrolysis of the PMHS DVB system. Gao did some work with not their own parameter set, but a parameter set developed by Newsom, looking at the pyrolysis of PMHS and HCPS systems. And then Vishis looked at mechanical properties in silicon oxycarbide fibers. So we want to extend this and look at ReaxFF parameters for SiCN PDCs. And in literature right now, there's no complete set for ReaxFF SiCN H. And so we propose to develop that. So our optimization method is pretty straightforward. What we do is we take our library of DFT computed crystalline and amorphous structures. We train our parameter set on those, and we follow the parameter optimization approach that Audrey von Duhn first used in his Reax code 2001. So because of the highly correlated nature of all these Reax parameters, for our set, it could be over 150 parameters that we're looking to optimize just for our four elements: silicon, carbon, nitrogen, hydrogen. So for all these parameters, there's supposedly very strong correlations that can occur between the parameters. So we choose a single parameter search to optimize our parameters, and we use a parabolic interpolation to find the minimum of our error surface. And we get our error by looking at our objective function as the combination of, if you see in the bottom, the error energy and the force error. So the energy due to error is only the difference between the Reax computed energy and the DFT computed energy. And it's fairly straightforward. Now, the force error is something we do by following the approach by Ercolesi, if I said that right, from the 90s, in which case all we really do is compare force as a vector. Or we really just compare the three components of the force vector in Reax and DFT. And this is some pretty standard stuff now. It didn't really catch on in the early 2000s, I think, but this is pretty standard stuff now whenever you're training any kind of machine learning potential or whatever you're training. So as we do this, we seek again to establish a correspondence between the Reax and DFT potential energy surfaces. And this is the main goal of training these energy and forces. But we're not going to really stick to the technical side here. Today, I'm going to talk more about how the current parameter set does with simulations of different polymers. So there are some issues with the current parameter set. So we'll look over what's good and what's bad that it does. So we do simulations with molecular dynamics. We do molecular dynamic simulations in LAMPS. And remember how I said earlier that we fit forces? Well, this is where it's kind of important, because molecular dynamics is the time evolution of a system, and it's governed by Newtonian mechanics. You can see how forces would be very important to get right in this case. And we do that. So we do constant pressure simulations at 2000 bar. This is following the approach Ilya had in 2019 to prevent the polymer from foaming before anything any solid kind starts forming. And then we use a time step of 0.4 femtoseconds. We change some parameters like charge equilibration and momentum rescaling to make sure we don't have any kind of flying ice cube problems. We don't do gas removal. So we'll stick more to a qualitative approach in this, although the simulations done here give a general idea of what reactions may occur, what a species may be formed, and what the final product may look like. So it's good enough in this case to observe the outcomes of the simulations. And our simulation scheme is on the right. So we start right away at 2000 Kelvin. We briefly hold it there, heat it up to 3000 Kelvin at 10 Kelvin per picosecond. Hold it for 3000 Kelvin for a while to really let stuff happen. And then cool down to 300 Kelvin at 10 Kelvin per picosecond. Okay, so looking at Saraset, we look at the Saraset polysiloxane 20 PSC 20 specifically, and you saw the different names that this would go by in Dr. Kroll's presentation. Here, I'll just refer to it as Saraset. So as you see from the structure of Saraset, 20% of the silicon has a methyl and vinyl group attached. The other 80% has only that methyl group, with the hydrogen still on the silicon. And on the right is how we model it. This is a single strand of Saraset. So there are periodic boundary conditions. The green atoms are nitrogen, or the green spheres are nitrogen. The blue, or I guess the blue is very hard to distinguish. The blue and black are going to be silicon and carbon respectively, and the pink shall be hydrogen. But you can kind of see how it looks like. This is, again, an infinitely long strand due to periodic boundary conditions. But now, since we're doing simulations with Reax, where we can go even bigger, we look at simulations with 8,500 atoms. So this is only a 4x4x4 supercell of what was just shown on the previous slide. So it's going to be 64 individual strands, and there's no need to cross-link them. We'll see what happens anyways, and the results shouldn't be impacted too much in this case. So you can see on the right, that's the structure, and we're going to look at it as we simulate it from 2000 to 3000 Kelvin. Here we go. So first, since it's at 2000 bar, there's going to be some shrinkage. I mean, there was a lot of open space, and now we can see the gaseous species forming. Don't worry, I'll play it again in case anything is missing. And we can even start to see some clusters of silicon, carbon, and nitrogen. Again, this is at high temperatures, so maybe you won't really be seeing any kind of solid, but we'll start seeing clusters. And the gaseous species that are formed are going to be predominantly ammonia. This is problematic, and I'll explain why throughout the course of the talk, but also hydrogen and methane, which is more of what you would expect. But again, a lot of ammonia. Here we go, let me play it again. So yeah, here we see again the decomposition of the polymer strands, the formation of the gaseous species. You'll see the little green and black balls flying around with their little attached hydrogen. And then again, the clustering of the silicon, carbon, and nitrogen. Okay. So now, after some long time at 3000 Kelvin, we have the structure on the right. And you can see now all these ammonia molecules that have formed. You can see methane too present in lesser quantity, and is a bit harder to see, but you could even find the hydrogen there, and they're quite small. So we look at it, what happens to the structure when it cools down, because we want to see what kind of resulting structures may form, if any form at all. So here it is. So we look at it, the clustering is still there. The gaseous species aren't removed, so they're going to stay there. Look at it again, specifically look at the agglomerate that we see on the right. So you're going to start seeing it form. It's going to start moving as one unit, right? So we'll call that an agglomerate right now. We can start seeing the formation of any kind of maybe bulk, but that's a different story. Okay, so now we look at what happens when we cool it even further. You see at the moment, the structure on the right is exactly as we saw it from the previous slide. All the gaseous species are persistent, and you would not expect this from ammonia because it is used as a reactive atmosphere anyways in a lot of experiments. But we go through it with it anyway, and we see what happens. You can start seeing that the agglomerates, there were maybe two before, have really merged together into a kind of chunk or rod-like structure. I'll play it again. This chunk exhibits silicon-nitrogen bonding, silicon-carbon, silicon-silicon, carbon-nitrogen, carbon-carbon bonding. All the hallmarks you expect to see in amorphous SiCN ceramics. So although we have very persistent ammonia, the bulk is coming out right. And with removal of gaseous species, it is very likely that the structure will be a 3D bulk extending in each of the dimensions, of course. All right, so now we look at how another parameter set in literature would do simulations to kind of give a comparison between what we can do and what is already there. Although this parameter set by Kulkarni is developed in 2013, was actually developed to study oxygen interactions with the silica surface. And it just coincidentally had silicon and nitrogen parameters, so it could do simulations of SiC and H. Now, there aren't any other parameter sets really that were doing the same thing we were doing, or really trying to simulate SiCN. So this is pretty much the best we can get as a comparison. And here I'll briefly show the same things I showed earlier. So now we just hold at 2000 Kelvin, kind of see what happens. Again, this is the collapse of the polymer, or not the collapse of the box, and maybe the formation of some gaseous species. Here you can see some hydrogen there. But that's not really super important because what we want to see is on the right. So this is the structure that results from long-term holding at 3000 Kelvin. And you see, it's not really a structure. This model contains lots of molecular fragments along with the gaseous species. So there was never any agglomeration like you saw with our parameter set. You will see it though, whenever we cool down, there will be some kinds of agglomeration. I mean, they're going to come together, and we'll look at the structure that does form in more detail on the next slide. Okay, so now we compare the outcomes of the Saraset simulations that we've done. So on the left is going to be a zoomed in view of the kind of agglomeration that forms in the Kulkarni potential, or the Kulkarni parameter set, and on the right is going to be our UTA parameter set. That's all I'll refer to it. So if we take a look at local coordination on the left, we have a lot of issues. We have over-coordinated carbon and nitrogen. Some weird things where nitrogen is in the center of like 6-membered rings. And it's not the Kulkarni parameter set's fault, because it was never designed to do these kinds of simulations. But this is what ends up occurring. You can see it occurs throughout a large portion of whatever is shown here, but also throughout the rest of any kind of SiCN ternary solid that forms. On the right, we have the outcome of our simulation, and we can take a close look at local bonding. So it's not like our parameter set is perfect, but it does avoid substantial issues that the Kulkarni parameter set had, though we do have a little bit of under coordination of silicon and a lot of long silicon carbon bonds, but that is something that can be addressed. So now we can kind of see the outcomes of different polysiloxanes, starting with polydimethyl polysiloxane. And we see the structure in the chemical formula on the left, and it's just going to be 2 methyl groups on your alternating silicon nitrogen backbone. So they're going to both be on the silicon, and you just have the end repeating units. On the right is our model of the polydimethyl polysiloxane. We can turn it. Again, with periodic boundary conditions, the structure or the polymer is intact, and it may only look a little bit of out of sorts. So we go ahead and see the final model after the simulation scheme. These are both going to be the same model, but on the left, you'll see all of the atoms. Well, you see all of the atoms, but it's hard to really see anything else. But we can take a look at it, and we see there's a lot of gaseous ammonia that has formed. Just like the Saraset simulation, we're going to see a lot of ammonia, methane, and hydrogen as well. Now on the right, once we don't really show any of the hydrogen atoms, and this kind of leaves some of the nitrogen and carbon from ammonia and methane stranded, that's okay. We can see any kind of maybe chunk that forms or agglomerate. And really, with the periodic boundary conditions, there's one kind of spheroid that forms. And just like the Saraset simulation with our parameters, it exhibits silicon carbon, silicon nitrogen, and all those bonds that are, again, the hallmarks of SiCN ceramics. Then we take a look at polydiphenyl polysiloxane. So just like polydimethyl polysiloxane, but we replace the methyls with the phenyl groups, and our model is on the right. You can really see those 6 rings pretty easily. Again, the structure is completely intact. If you look at the composition, right, this number of atoms and the SiCNH in the bottom, you can see that there's a lot more carbon atoms than there are silicon atoms, and what we're really looking for is maybe the formation of any kind of free carbon structure whenever we do simulations. So we go ahead and apply our simulation scheme to the polydiphenyl polysiloxane, do those molecular dynamic simulations, and we get a resulting structure that you see on the right. And I've already taken care of the hydrogen atoms, but there's a lot of carbon anyway, so you'd be able to see it. So if we take the rotation, we can see already the most carbon is bonded to other carbon. We can see the formation of rings, a lot of 6 rings too. And based on that, it is likely that either with longer simulation time at elevated temperature or gas removal, that a extended carbon network can form. And that's something we're also very interested in looking at. Okay, so that's it. In summary, we looked at simulations of different polysiloxanes. We found that with our parameters, we can avoid issues that are present in the existing parameter sets, especially some of those weird bonding situations that occurred with simulations of the Kulkarni potential. We look at the formation of the different gaseous species that occur, and we do see the hydrogen and methane that you'd expect. We see ammonia, but we see a lot of ammonia. And this overabundance of ammonia is actually quite persistent, and it's something that needs to be addressed. Fortunately, we already have kind of worked on that, although this new force field requires, or new parameter set requires, a little bit more extensive testing. So by better fitting these nitrogen and hydrogen parameters, we get the structure on the right. This is Sarah said, it's in the middle of a simulation. Again, you see the formation of any kind of agglomerates, but the gaseous species that you find scattered throughout the box are almost entirely methane. There's hydrogen actually, and there's a very little amount of ammonia. So we can kind of start taking care of that, though it does lead to some interesting new issues in terms of local bonding and coordination. In any case, our future work is really going to be describing the reactivity of gaseous species better. So that's it. I'd like to thank my research group, the NSF PIRE project for funding, of course, the UTA Department of Chemistry and Biochemistry, and the UTA Graduate School for a bit of extra funding this semester, as well as the Texas Advanced Computing Center, San Diego Supercomputer Center, and the UTA High Performance Computing Center for computing resources.